In this last video, we'll consider a couple of interesting problems. This one, we have a 50-kilogram woman that's walking across a canoe. That seems pretty likely, doesn't it? From 1 meter from one end to 1 meter from the other end. And here's the dimensions. We have the entire canoe is 1 plus 1 plus 3 is 5 meters. And the canoe's mass is 40 kilograms. So she's going to go from her position here at 1 meter from the end and walk along here, in high heels of course, to 1 meter from the other end. And we're going to try and determine, not try, we will determine the motion of the canoe through the water, how much the canoe moves during that process. And the canoe is assumed to move through water effortlessly. So the position of the center mass, we just have to worry about the x direction here. So we consider the mass of the woman and the mass of the canoe from x is equal to 0. So let's go ahead and put the numbers in. And it looks like 50 times negative 1.5, because that's where she is, plus 0, because the center mass of the canoe is at 0, over total mass of 90, gives us minus 0.833 meters. Right there. Now it's a very important and key point to these kind of problems is that the center of mass in a frictionless medium like this, which basically means there's no external forces, it's just internal forces, that position of the center of mass will remain fixed in space. So it's not going to change. So when we get the center of mass at different positions as the woman walks across, we know that center of mass location still has to reside at minus 0.833 meters. So that'll help us to understand how far the canoe is moved. So here at an intermediate point, I don't have a good way to make her disappear here, but when she's at the center mass of the canoe, so the center mass of the canoe and her are right at the same place, that center mass has to be where it was before. So the whole system has to shift to the left. So it does. It shifts to the left 0.833 meters. Then when she moves all the way over to her final destination, 1 meter from the other end of the canoe, the new center of mass is 0.833 meters positive, if you just consider the symmetry. She started here, ended here. So this distance and this distance are the same from the center mass of the canoe. And we have a total shift of the canoe represented by this green arrow here. So because of symmetry, it helps us understand what's going on here. We basically have flipped the system about the center of mass. So here is the canoe represented with a rectangle, center mass right here. And it's been shifted 0.833 meters to the left because of the woman. So that's really where the center mass of the system is. And now we see that as she moves to her final destination, the center mass is moved from here all the way over to here. And that turns out to be a total distance of 1.67 meters. This is really the same thing that would happen is if you had an asymmetrical object and you threw it in the air like a hatchet or a hammer. It would rotate about its center of mass, and when you flip it around 180 degrees, the relative positions switch in a manner similar to what's going on here. So in that case, it tends to be a little top heavy or head heavy, which shifts the center mass from the center of the object over to one side. And then when it rotates in the air, it rotates about that center mass as it flips through the air. Ready for a slightly more challenging problem? Let's go for it. We have a semicircular plate, and we're going to find the center mass of the semicircular plate. Obviously, there's symmetry in the x direction. So we know that the center mass is going to lie along this axis here, along the line of symmetry. But how far in the y direction is the center mass going to lie? So that's not necessarily so easy. Mass is density times volume, and the volume of this semicircular plate is simply the area of a circle times the thickness divided by 2. So there's 1/2 pi a squared times the thickness. Multiply that by the density, and you have the volume. I'm sorry, you have the mass. So from symmetry, we know xcm is equal to 0. We're just going to call that x is equal to 0 here. Now, we have to use the generalized version of the center mass for y, 1 over m integral of y dm. But we need dm in terms of dy. How do we get that? Again, we can't just utilize this as it stands. So we're going to do that is look at the geometry here a little bit. So we have the semicircle and a, and here's the height y, and that can be specified in terms of a because the distance from in the x direction based on how high it is and a is simply, this is a right triangle, so we can use Pythagorean theorem, and so the length of this side, that's the length of x, is equal to square root of a squared minus y squared. So here's a little segment, a cross section of this semicircular plate. Take a cross section through this whole thing. Then that's what this is. So we have the width being twice this length, and we have the thickness, and we have, I'm sorry, the width, which is t, I guess that actually is, you can call it the thickness, and then this dy is a differential thickness of the plate in that dimension. So don't get the thickness terms interchanged there. So we have that differential mass is equal to rho dV. So dm is rho dV. Density times volume. Differential volume will give you the differential mass. And it is simply the density times the differential volume. The differential volume is this dimension, that's 2 rad a squared minus y squared, times the thickness times dy. So all those things are included here. Everything is there. So that is dm. And now we can solve for the center mass in the y direction. 1 over m integral of y dm. And dm has already been solved in terms of dy, is this expression here. So that's pretty nice. Keep in mind m is density times volume, which is density times volume, 1/2 pi a squared t, which we already solved. And that's useful because we're going to sub that in for the m, because we don't want the center mass in terms of the mass. Not at all. We want it in terms of more fundamental quantities that are more generally applicable. So y center mass, plugging in m for m, this expression, and the 2 comes up here. So we have the same thing in the radicand. The densities go away, the thickness goes away. So this simplifies to this expression. 4 comes up here. And what we have here is something that we need to simplify a little bit. So we can do that by letting u equal to a squared minus y squared. And then, of course, du is negative 2y dy. And now the y center mass is reduced to this expression, which has y, u to the 1/2, because y is y, and square root of a squared minus y squared is square root of u. dy is du over minus 2y. So nicely, the y's go away, and the minus 2 is canceling out with a 4. Leaves us a minus 2 over pi a squared integral of u to the 1/2 du, which is minus 2 over pi a squared. U to the 1/2, when you integrate that, you get 2/3 u to the 3/2. Hey, Pay attention. Quit zoning out on me here. We're almost done, so stay focused. All right, that's minus 4/3, 4 over 3 pi a squared, u to the 3 halves. And now it's time to stick our result for u back in. Of course, that's a squared minus y squared for u. So there it is. And now when we do that little bit of math, when we plug in a for y squared and we plug in 0 for y squared, we get this. This whole expression is just gone, and the remaining expression is a squared to the 3 halves power. Well, the 2's go away, so we have a to the 3rd, but we have a squared underneath here, so that makes 2 of them go away. And we end up with our coveted result, 4a over 3 pi. And I hope you found some pleasure and satisfaction in solving that problem.